Math Olympiad 2022 problem T7. At first, let's have a look on the problem statement. We are asked to find all functions from the positive integers to the positive integers such that f of 1 is less than or equal to f of 2 is less than or equal to f of 3 and so on, and f of n plus 1 is equal to a squared, where a is a positive integer, and f of n minus f of n is equal to b squared, where b is also a positive integer. The main difficulty in this problem is to deal with these f of n terms and the f of n term in our two equations, because it's very hard to say how large these terms are, and therefore we can't really say something about if these terms are perfect squares or not. Thus, the idea is to combine these two equations and to get rid of some of these f of n terms. So, if we have a closer look on these two equations, we can come up with the idea to put in f of n in equation 1, and then we get that f of n plus f of n plus 1 is equal to a squared. This is nice because now we have f of n in our equation 2, and we have f of n in this new equation, and therefore if we subtract equation 2 from this, we can get rid of this f of n term. So let's write this down. We make this equation minus 2, and then we get that the f of n term cancels out. Then we have f of n minus f of n, which is 2 times f of n, and then we have a plus 1, and this is equal to a squared minus b squared. And here we see that the left hand side is positive, and therefore a must be greater than b, so we can say that this is greater than or equal to b plus 1 squared minus b squared, since both a and b are positive integers. Now this is equal to b squared plus 2b plus 1 minus b squared, and here the b squared cancels out, and therefore this is equal to 2b plus 1. Now we see that we have 2 times f of n plus 1 on the left hand side and 2b plus 1 on the right hand side, and therefore we directly get that f of n is greater than or equal to b. Plugging in this back into our equation 2 gives us that f of n minus f of n is equal to b squared. This is less than or equal to f of n squared. And now we can bring the f of n onto the right hand side, and we get that f of n is less than or equal to f of n squared plus f of n. So we found our first bound on our function. After finding an upper bound, our next idea is to find also some lower bound for our function, and therefore to get a better understanding how these two equations work, we may plug in some values. And we use equation 1 for this because in equation 2 we have this f of n term, and it's very hard to handle this term, and therefore it's a better idea to use equation 1. Okay, so let's start with plugging in n equals 1. This yields f of 1 plus 2 is equal to a squared. And here we see that since a squared is a perfect square, this must be at least 4, and therefore f of 1 is greater than or equal to 2. Okay, let's plug in also n equals 2 in this equation. This gives us that f of 2 plus 3 is equal to a squared. This time I have to note that this is not equal to the a squared here, and since we already figured out that f of 1 is greater than or equal to 2, and since we have that the function is increasing, we know that f of 2 is also greater than or equal to 2. Therefore, the left hand side is greater than or equal to 5, and Since it is a perfect square, a squared must be at least 9. Therefore, we get that f of 2 is greater than or equal to 6. Now, let's plug in a last value for n in the equation and take n equals 3. This gives us that f of 3 plus 4 is equal to another a squared. And here with the same argument, we have that f of 3 is greater than or equal to f of 2, and f of 2 is greater than or equal to 6. Therefore, the sum here is greater than or equal to 10, and the smallest perfect square greater than or equal to 10 is 16. Therefore, a squared is at least 16, and we get that f of 3 must be greater than or equal to 12. So f of 3 is greater than or equal to 12. Now, if we have a look back to our inequality here, we see that for some arguments of our function, we can bound the function by the polynomial x squared plus x on the right hand side. Therefore, maybe we want to try to write these numbers in the same form than here. And indeed, this is possible because 2 is the same as 1 squared plus 1, 6 is the same as 2 squared plus 2, and 12 is the same as 3 squared plus 3. So we can indeed bound our function for the first 3 terms by the polynomial x squared plus x, and therefore our guess is that in general f of n is greater than or equal to n squared plus n. In order to prove this, we have a look back to our examples here, and we remember that when we figured out that f of 2 is greater than or equal to 6, our argument was that since f of 1 is greater than or equal to 2, and since f of 2 is greater than or equal to 1, we have f of 2 plus 3 is greater than or equal to 5. And therefore the least square, which is greater than or equal to 5, is 9. And here we see that the left hand side was 5, which is exactly a square number plus 1. This might seem as a coincidence, but if we have a look back to the equation here, we see that this 2 is exactly 1 less than the 3, and we plug in the same value for f of 2 than for f of 1 here, and therefore this left hand side here is at least this a squared plus 1, and thus we can indeed see that this is not only a coincidence, and that is true for every integer we plug in here. Thus, we want to try to prove that if n grows in our equation 1, then also a must grow. And since we know that the left hand side is a perfect square, we can have a look on the square root of the left hand side, and we know that it is an integer. So let's write down the square root of f of n plus 1 plus n plus 1 plus 1, which is the left hand side of the equation here with n plus 1 instead of n. And here we know that this is greater than the square root of f of n plus n plus 1. This is because by f of 1 is less than or equal to f of 2, and so on, we know that f of n plus 1 is greater than or equal to f of n, and we see that n plus 1 is greater than n plus 1. And since we have that these terms here must be integers, we can write down plus 1 onto this term and write a greater than or equal sign, because the distance between two integers is at least 1. So now we want to use this inequality here to find a lower bound for f of n, and therefore we start with this term here and write down that square root of f of n plus 1 is greater than or equal to the square root of f of n minus 1 plus n minus 1 plus 1, and here we use this inequality and get a plus 1. Now we use this inequality again and get that this is greater than or equal to the square root of f of n minus 2 plus n minus 2 plus 1, and now we have a plus 2 outside this square root, and now we do this up to the square root of f of 1 plus 1 plus 1, and here we have a plus n minus 1 outside the square root. And since we already figured out that f of 1 is greater than or equal to 2, we can write this as the square root of 4 plus n minus 1, and this is in total n plus 1. Now we can square both sides and get that f of n plus n plus 1 is greater than or equal to n plus 1 squared, which is equal to n squared plus 2n plus 1. And now, if we subtract n plus 1 from both sides, we get that f of n is indeed greater than or equal to n squared plus n. So we get that f of n is less than or equal to f of n squared plus f of n, and we also get that f of n is greater than or equal to n squared plus n. And now if we plug in n equals f of n into the second inequality, we get that equality must hold, because the first one says that the left hand side is less than or equal to the right hand side, and the second one says that the left hand side is greater than or equal to the right hand side. So we get that f of n is equal to f of n squared plus f of n. Moreover, we know that our function is increasing, and we also know that f of n is greater than or equal to n squared plus n, so our function is not bounded, and thus, since for some values of n we know that the value of the function is equal to n squared plus n, we get that for every big X from the natural numbers we can find some small x greater than big X, such that f of x is equal to x squared plus x. Now, our obvious guess is that f of n is equal to n squared plus n is the only solution for our problem. And in order to prove this, let's assume that there is some n for which f of n is not equal to n squared plus n, but since we already figured out that f of n is greater than or equal to n squared plus n, we can assume that f of n is greater to n squared plus n. Now let big X be equal to n, then we know that we can find some small x which is greater than big X, and therefore small x is greater than n. And now we can use our identity here we found before, and from this we get that x plus 1, which is equal to the square root of x plus 1 squared, which is equal to the square root of x squared plus x plus 1, which is equal to the square root of f of x plus 1, is now, from this identity, greater than or equal to the square root of f of x minus 1 plus x minus 1 plus 1, and plus 1 outside the square root. Now this is greater than or equal to the square root of f of x minus 2 plus x minus 2 plus 1, and now our plus 2 after the square root, and now we repeat this, x minus n times, and in the end we get that this is greater than or equal to the square root of f of n plus 1 plus x minus n. And now, since we figured out that f of n is greater than n squared plus n, we can write that this is greater than the square root of n squared plus 2n plus 1 plus x minus n. And now here we know that the square root of n squared plus 2n plus 1 is equal to n plus 1, so this is equal to n plus 1, and now plus x minus n. So the n cancels out and we end up with x plus 1. So overall we have that x plus 1 is greater than x plus 1, and this is obviously a contradiction. Therefore f of n is greater than n squared plus n. It's not possible, and so our only possible solution is f of n is equal to n squared plus n. And now it's only left to prove that this function also works. In order to see that f of n is equal to n squared plus n is indeed a solution, we must plug in f of n into equation 1 and 2. So let's start with equation 1. Here we get that n squared plus n plus 1 is equal to n plus 1 squared. So this is indeed a square, and thus equation 1 is satisfied. And now let's put in f of n into the second equation. Here we get that f of n is equal to f of n squared plus n, and here we have minus n squared plus n, and now f of n squared plus n is equal to n squared plus n all squared plus n squared plus n, and now we subtract again n squared minus n, and we see that this cancels out, and we have left n squared plus n all squared, and thus this is a square, and therefore also equation 2 is satisfied, and we are done.